you.
Well, thank you very much for that kind invitation, Sven, and it's really a privilege to be here. As Sven alluded to, I've been in the business of quantum computing for more than 25 years, and it really feels great to be giving this talk for the first time at UNSW, where it all really began for me. I was going to hand my PhD in experimental physics back in to University of New South Wales whilst I'm here if I couldn't figure out the AV, and the good news is that I'm close now. PhD in experimental physics, safe for now, but it could be revoked at any point. And yeah, there's two paths really I want to try and cover for you today in the spirit of the Westheimer lecture, which is this sort of technological scientific path, but also a bit my own path and the path of the organization that got there. And so, you know, along the way, I'm going to tell you a little bit about what I think may be the path to a useful quantum computer in my lifetime, and I'm also going to tell you a little bit about my journey there. Before I get going, I just want to pause for a minute. I have 2 degrees from the University of New South Wales, one a science degree and one a PhD in physics. I think I was saying to someone before, I think I'm a semester away from a philosophy degree, and during my philosophy studies I had the privilege of studying history and philosophy of science and technology, very interesting subjects. And I think I want to just sort of pause for a minute and have us, think about these things that we now carry around in our pocket. And I think we humans are prone to both taking for granted the advanced technology that we have, and also lacking imagination about what more there could be to come, and they seem to be somewhat contradictory to me. And, you think about these things that I'm showing here, nuclear energy, robotics, semiconductor manufacturing, supersonic flight, genomics. These were all things of science fiction not so long ago, in living memory for some people in this room. Those things were science fiction, and they've all become reality in the last 50 years or so. And these types of innovations, and by extension I would argue a large fraction of Fortune 500 companies, car companies, material companies, energy companies, etc., were made possible thanks to human mastery of our physical world. And it's really the ability to simulate, calculate, understand, and predict the behavior of materials, chemistry, physics, and information that is really fundamentally important to bringing these technologies into reality. So, I think it's fair to say that an increasing number of people believe that quantum computing could be the single most impactful machine that humans could build in order to categorically advance our mastery of our physical world and information. And I want to just take a quick dive into one area of that. How many people here are chemists by trade or by training? Okay, so there's a few of you, and if you all rush me at once, I could be in trouble, but I suspect you'll only do it one at a time. I would contend that we can't, in fact, start to do chemistry until we have a quantum computer. That's designed to be deliberately provocative, but it's also designed to be deliberately true in the sense that if you can't simulate the building blocks of the world that you find around you, never mind the building blocks of the systems that you would like to engineer yourself, what are you really doing there? And that is what we're doing in chemistry. And if you want some sort of evidence for this outrageous claim, then you need to look no further than the world around you and life within it. We humans got given the same chemistry set that life got given. Life took, several billion years of evolution to be able to do things that make us look like absolute rank amateurs, right? The things that life can do on a chemical front. There's no, in principle, reason why we couldn't be able to do the same things. And a big impediment to that is that we can't simulate the properties of, at the molecular scale. And that's just one area that we understand increasingly well how we'll be able to use quantum computing in that. So does anyone know what this is here? Yeah, this is a quantum computer from a science fiction TV show, and you see it in the standard semi-religious type of setting, super powerful machine that's going to change the world. And the problem that I've really spent my life so far trying to solve is that quantum computing is indeed very much in the regime of science fiction. Here's what, in my opinion, is the most impressive existing quantum computer on the planet today. This is Google's system in Southern California. And on the one hand, it's really very impressive. A chip the size of your thumbnail, approximately, with about 72 qubits. So qubits are the transistors in a quantum computer. So a tiny chip of that size with just 72 qubits is able to outperform a building-scale billion-dollar supercomputer. So that's a really impressive feat. There's been some dispute about that, and Google have put more qubits into the task and settled that dispute. But that's a profoundly important scientific achievement. But on the other hand, you can see a problem, which is that this really looks like a science experiment that belongs in a research laboratory, that's cooled to 100th of the temperature of deep space and sort of wired up by hand and so on. It looks like it's born to live in a laboratory. But the real problem is that it's useless. So what you don't necessarily read about in the newspaper story that accompanies these sorts of breakthroughs is the fact that no one has figured out how to take a system of this sort of scale and deploy it for anything useful. And so if you happen to be amongst the people who know that quantum computing is at this stage of very early science fiction, it might surprise you to hear that my company, PsiQuantum, is today manufacturing millions of components in the flagship production line of one of the most advanced semiconductor fabrication facilities on the planet. So this that you see in this video here, this is Global Foundry's Fab 8, which is in Malta, in New York. And this is the same sort of category as TSMC and Samsung and Intel. These are the factories, of which there are very few, that make the advanced chips that go into your, into these laptops and mobile phones and cars and everything else these days. And for a few years now, we've been building quantum devices, entangled photon sources, superconducting single photon detectors, etc., in this facility. And I just want to quickly give you an overview of how we got to that point. So, in brief, how we got from the university research environment with a researcher here with a small chip under test, manually operating things. This chip, in fact, was put on the cloud as, I think, the first quantum processor, 2-qubit processor, back in 2013. It's now in the British Science Museum next to a Babbage difference engine and an Enigma machine, which is a good place for it because it's a museum piece. It was fun, but it didn't really address the real challenges to building a utility scale system. And the sort of ethos that I had and my co-founders had and our company has to this day is to really understand this picture, which comes from my colleagues at Google, and I'll just talk you through it somewhat briefly here. So it's showing you for the size of your quantum computer, so from 1 qubit, remember they're the equivalent of the transistors in a quantum computer, so from 1 qubit to millions of qubits, and for very high quality qubits down here to very low quality qubits up here. So you can think of this as a plot of the size and quality of your quantum computer. And it's showing you what you can and can't do in various regions of this space. So for small numbers of qubits and or large error rates or poor quality qubits, you can simply simulate your quantum computer on a conventional computer. And so Google gives you a big cross here, nothing interesting to do there. And that demonstration that I just sketched of Google was crossing out of that purple region into this blue region in a demonstration of so-called quantum supremacy, so a very poor terminology developed by a very brilliant colleague of mine, John Preskill at Caltech, because what it means is that outperformance of a conventional computer that I described before. And a lot of the world of quantum computing, and I would say that UNSW has been a standout exception to this, but a lot of the world of quantum computing has been focused on how could we do something useful here. Hopefully we can do something useful, and so far no one has found anything useful to do in that regime of, let's say, 100 to 1,000 qubits. And you won't read that in the newspaper, you might not read that in the scientific paper, but it is a fact of the world that no one has a recipe for how to do something useful there. We, as a company, made a bet that, yep, all of the action is up here. You really need to be in that error-corrected regime with, therefore, of order millions of qubits, and therefore in a tier 1 semiconductor foundry from the start. And we were regarded as fringe lunatics for the first couple of years that we were operating as an organization, because we were just adamant that we have to head there, and we have indeed spent every minute and every cent heading in that direction. And I'm glad we did, because the way I would sort of summarize it is with this cartoon here, and those of you who know me will know that I deal mostly in glib cartoons, and those of you who don't, well, I'm telling you that now. The point here is that, in some sense, these two systems do the same thing, right? Powered flight. But, one is a commercial technology, and one is a proof of principle that you can demonstrate powered flight. And obviously, there's quite a few decades and probably quite a few $1 billion between these two things, and that's the gap that really needs to get closed. And I'm really gratified that the quantum computing industry is really facing up to those facts now. So I'm not going to go through this in any sort of detail, but the way my co-founder Pete likes to put it is, don't worry about the qubits. Everyone's got qubits. Everyone's had qubits for decades. The qubits are fine. People have got qubits. They're entangled. They're running gates on them. They're doing small-scale algorithms, whatever. Qubits are not the problem. The problems are the scaling challenges between dozens of qubits and millions of qubits. And I've enumerated those challenges here. I've highlighted that manufacturing component of it, and the cooling power, connectivity are reasonably self-explanatory. As you probably know, many of these quantum computing systems need to operate at very low temperatures, so you need to have a sufficient amount of cooling power to cool those systems to the temperatures that they need to operate at. And that's not challenging if those temperatures are tens of millidegrees Kelvin above absolute zero, for example. Any type of quantum computer with millions of qubits is going to be an extensive system and needs to be wired up. And you can't just use USB cables to wire up a quantum computer. You need quantum interconnects to wire it up. And then finally, a system of that scale and complexity, unsurprisingly, requires a whole bunch of conventional control electronics with it as well. And some of those control electronics need to be proximate to the qubits themselves, and therefore of a commensurate density and a compatible operating environment. These are the challenges that stand between where we are today with proofs of principle, the first demonstration of powered flight, and a commercial technology. And so at PsiQuantum, we don't necessarily like the photonic approach to quantum computing because photons make better qubits. They make great qubits. I love them as qubits, but I also love plenty of other qubits. What I really like photons for is the orders of magnitude advantages that they have in these scaling challenges. I hope that gives you a bit of a flavor of the technical issues that are being addressed. And I'll get briefly a little bit more technical here and sort of sketch to you how we envisage bringing one of those million qubit systems into reality, which is depicted here in cartoon form on the left. And you should imagine this, these cabinets, if you like, are very much like a sort of the 19-inch rack scale module, so a bit taller than me and a bit wider than me, that you would see in a data center or in a high-performance computer. That sort of scale of module is what you're looking at here, and you're looking at many dozens of them wired together in a facility that indeed looks very much like a data center. The way you get there is you take a small number of silicon photonic components, so beam splitters, single photon sources, detectors, so on. You manufacture them through the integration of a whole bunch of materials in what is now a very standard method for creating the chips that go into these things. There's a lot of complexity in being able to do that. Then you package those photonic chips up with electronic chips, and you wire that all together optically and electrically, and then you assemble those packages into those cabinets, and those cabinets into the full system. So hopefully that gives you at least a high-level overview of how these things come together. Now, at PsiQuantum, we've made millions of these components. We've made thousands of wafers of material. We've made hundreds of these packages, and we'll start assembling, I'll show you in a moment, the first of these systems this year, and then we'll begin assembling this array. And so that's why we believe that we're very close to getting this job done. So, here's a wafer with, covered in photonic components. It's mostly pretty boring from a quantum physics type of perspective, and that's how it should be from my perspective, although it's actually a truly remarkable manufacturing capability that we humans have developed. It's cost us about $1 trillion and 50 years to develop that technology. So it'd want to be pretty darn good, and it is pretty darn good. But it's also pretty standard in the sense that, we humans are producing billions of these chips with billions of components on them in a routine fashion, so that they're basically a commodity that go into all of our devices and systems. And that's been our ethos as an organization, is that it should be a boring technology. It should be familiar, because if it's not, you're not very close to a real working system and a real technology. Now, there are exceptions. And I want to talk to you about one very recent one. So one of the things that we were missing was a very high-performance optical switch, so a very low-loss, very high-speed optical switch for routing photons on the chip. And what you see here is a facility that we built in San Jose. This is a molecular beam epitaxy system. It's the only 300 millimeter wafer molecular beam epitaxy system on the planet. It operates in that high manufacturing type environment, such that cassettes of 25 of those wafers can be incorporated into global foundries. It's got molten titanium in it, and things cooled to Kelvin, several Kelvin, so several degrees above absolute zero. We took a huge bet on this one, and we paid a lot of money for this facility and everything that goes in it. And we're very glad that we did, because it's just started to pay off in the second half of last year and this year, where we're now producing the most advanced optoelectronic films on the planet, and we're shipping them to global foundries, and we're making devices out of those films. And so, to zoom out for a second, we are soon then exiting the sort of semiconductor manufacturing phase of the operation of the company, if you like. You can think of the science as being done in the 20 years prior to founding this company. We've spent the last 7 years and several hundreds of millions of dollars, tackling the semiconductor engineering part of things, and we're soon to enter into the infrastructure phase of things, which is big and scary. I think I'll ask for your help on some of that large-scale infrastructure. But the point is that I'd rather have cement and concrete and kilometers of optical fiber type problems than I would, quantum physics type problems. And Along the way, we're scaling up the cryogenic system. So this is what we currently use at the moment. We are able to test individual PCBs, so individual packages in those systems. We're rapidly moving on beyond that, so to these bigger systems that have significantly more cooling power. And we're sort of at this pace of an order of magnitude per year, if you like, on course to these cabinets. Now, I don't know about you all, but when I see these beautiful renderings, I'm often unimpressed, because I think that just shows that you know how to use a computer and you can draw a nice picture. Especially in the age of AI, I think even my 12-year-old son will be doing that on a routine basis. So I'm really happy to be able to share with you that we've commandeered this retired particle accelerator in the British countryside, and using the cryogenic capability that's existing there, and we've built this system, and we're aiming to fire it up later this year. So at that point, I'm just going to pause and switch gear a little bit and tell you a little bit about how I got to the point where we have a company that's building some of the largest scale sort of cryo systems that you can hope for, and leap back to 1997, where as a undergraduate honors student at UNSW in physics, this was a cryostat one of many cryostats that we blew to pieces using these high explosives here in the desert in New Mexico, and which was quite something to do as an undergraduate student. And it started for me when I started my undergraduate studies at the University of Western Australia before I moved to UNSW. And in my second year of studies, I got a hold of this magazine. And that was 1995. Those of you with good eyes can see that it's dated 1994. But back in the mid-90s, it took about a year for a magazine to get to Perth. And so we got a hold of it in 95. And in this magazine is a description of how if you could harness quantum mechanics and build a quantum computer, you could bring about a revolution that would be comparable to fire or agriculture or steam power or digital revolution or something. And all of us in this quantum mechanics class thought, this is mad. Like, first of all, this is madness what we're learning in quantum mechanics. We're second-year undergraduate physics students learning quantum mechanics for the first time. And wow, it could actually be not just be useful, but profoundly useful. And so I moved to the University of New South Wales, and this was one of very few and probably the only places on the planet that you could study a PhD in building a quantum computer back in those days. And this was an approach that we started way back, and that Michelle Simmons is still the world's leading exponent of back in the day. So using single phosphorus donor atoms as qubits. I got to the point where I was really obsessed with how are we going to get to 1 million qubits. We got to get to 1 million qubits, and having spent sort of 6 years on that journey, at some point I was sort of looking at all of these different approaches, and I had job offers from NEC in Japan, who had the best superconducting qubits in those days, from NTT in Japan, who had very good quantum dot qubits in those days. And I was sort of, I spent a week in both places tossing up between the two. And around that time, it was around 2001, a draft of this manuscript landed on my desk, because Gerald Milburn, who's the last author on this paper, was the deputy director of the research centre, the National Australian Research Centre in Quantum Computing, that my PhD supervisor, Bob Clark, was the director of. So I got early sight of this manuscript, which said something that was absolutely fantastical, which is that you could build a quantum computer out of photons, not out of electrons or matter-based systems or so on, but you could build a quantum computer out of photons. That was the theoretical result. So I managed to talk my way into a postdoc with this gentleman here, despite without exaggeration, not knowing which end of a laser light was going to come out of, I got a job in a quantum optics laboratory, and that was a pretty special place, Queensland today. So Gerald, one of the authors on that paper, was there. Andrew had just returned from Los Alamos. Tim Ralph was a sort of bridge between the theory and experiment. Mike Nielsen, who the young people in the room will all have a copy of this book, and the old people in the room, I'm looking at you, Andrea, will also have a copy of this book, because it's an unusual book that is both the de facto standard textbook for undergraduate courses and also the de facto standard reference book on the topic, which is extraordinary. And these two guys are professors somewhere across the city these days, Steve Bartlett and Andrew Doherty, and Jeff was my arch collaborator, so it was special times. And we indeed made the first inroads into photonic quantum computing, demonstrating the principles of this paper. But in order to go from demonstrations that look like this to really putting it on a chip, which was the clear route to making this whole thing scalable and manufacturable, that took me to the other side of the world, to the University of Bristol, where we were able to make some real headway on that, developing this approach to integrated quantum photonics, having a lot of fun doing that, but all the time sort of being mindful that there were really big challenges that we had to tackle. And everything changed in 2015, and the way things changed in 2015, so I had been at it for about 20 years at that point, and this is my thesis, which was shared by plenty of other folk here at UNSW back in the mid to late 90s and to this day, was that we're just not going to, it's just not going to happen in my lifetime unless we figure out how to leverage the semiconductor industry. Because otherwise, you're going to have to spend a good fraction of those 50 years and a good fraction of $1 trillion at least to create an equivalent manufacturing capability. And in 2015, we had an architecture that we believed satisfied that requirement. In the short history of the company is we spent the first several years and several $100 million actually getting into one of those tier one semiconductor foundries, and now we've been working with them for several years, and we're close to starting to pour the concrete to build that facility that I've sketched for you. I won't say much more about the journey along the way of starting a company. This is an early photo that brings fond memories to me. This is the entire company, and of course, as you go from zero to several hundred people, obviously you need a bigger and bigger room to fit everyone in a wider and wider lens. But the more important thing is that there's an incredible people story associated with all of this technology. I want to finish with a non-people story, the anti-people story. So this is a piece of automated test equipment. It's pretty standard in the semiconductor industry. And I had fantasies about this equipment for many years when I was a professor of physics. And what you can see it's doing here is it's taking cassettes full of 25 silicon wafers. Each of those wafers is covered with hundreds of chips before they're diced up and turned into individual chips. It loads those things automatically. It comes along, it tests all of the components on them. It maps out the performance of these things. And when the first one of these things arrived, I did a back-of-the-envelope calculation, and I estimated that it does the job of about 100,000 graduate students, one of these machines. I think that was before we put the auto cassette loader on it. We soon got a second machine. We've just got another 4 of 6 of these things arriving. And this is both sort of an incredible transformation from my perspective, from being in a research lab, myself or my grad students doing things by hand, to using the state-of-the-art tools of industry. And it's also absolutely necessary, because if you're going to build a system with millions to billions of components, you're going to need to test billions of components along the way. And if you're going to do that by hand, one by one, that's going to take a very long time indeed. And so it's very exciting to be able to do a lot of that work here. And so for me, it's one of those moments in in history that I'll just never forget, walking in and seeing one of these things in our facility. And now, of course, they're just a sort of like a coffee machine, just a routine thing that people do. All right, I think I've used more time than I would have liked, but let me stop there and thank you for your attention and thank you for the opportunity to talk to you.